Hello again. This time around, we're going to take a look at trigonometric equations. So um, specifically, we want to know how to solve equations where the variable is in the argument of a trig function. So this is a useful skill because we use trig functions to model um, real world data, and then we use those models to make predictions, for example. So um, let's say you have a sinusoidal model for the average daily temperature in a particular region of the world. Um, and let's say you're curious, you use that model, you're like, okay, so when would the next time that I can expect the temperature, the average temperature to be, 65 degrees Fahrenheit? Well, then I would plug 65 degrees Fahrenheit into the output of that function, leaving an equation where I need to solve for the input, which is that variable would be part of the argument of the trig function. So I would need to know how to solve an equation where the variable is in the argument of a trig function. So that's what we're going to take a look at, is how to solve such equations. All right, so let's kind of set the stage for what's about to happen. So let's go back to equations we already know how to solve. So let's go back to like a quadratic equation. You guys have been solving quadratic equations since algebra 2 specifically. And let's talk about how we would solve this. So if I wanted to solve this analytically or algebraically, I would take the original equation, which is right here. And in this case, I might try to factor it. It's a quadratic. Quadratic sometimes factor using integers. So I would move everything to one side. So now I have this where everything's on one side. It equals 0. And then I would attempt to factor that quadratic. X squared plus 6 plus 8. X squared plus 6x plus 8 factors into x plus 4 and x plus 2. Well, now I have the product of two numbers equals 0. Well, according to the zero product property, either that first number has to be 0, so then x needs to be -4, or the second number, second factor, has to be 0, so x needs to be -2. So it turns out as long as x is -4 or -2, this statement will be true, which means this statement will be true, which means this statement is true. So x is -4 or x is -2. So it turns out of all the real numbers in the domain of this function, there are two such numbers that make this a true statement. Every other number makes this a false statement. So that's important here, that the domain of the function that's involved here is all real numbers. So x squared plus 6x, that's a quadratic function. Its domain's all real numbers. But there are only two real numbers in that domain that make this a true statement. It's -4 and it's -2. Every other number in the domain makes this a false statement. But that's just one way we could have solved it. Another way we could have solved it is we could have graphed it. So I could have graphed x squared plus 6x plus 8. I'm sorry, x squared plus 6x, which is right here. So I could have graphed this function, which is right here. And then I could have graphed this function, y equals -8, which is right here. And then I want those to equal each other. In other words, I want to know for what x value will they have the same output. So for what x will this equal -8? Well, it turns out it does it twice, right here and right here. So the points at which they intersect tell me that for x equals -4, I get an output of -8. So -4 must be one of the solutions. But also when x is -2, I get an output of -8. So -2 is also a solution. So it turns out I could actually just graph the left side and the right side and see where they intersect, and that tells me my answers also. So there's my x equals -4, and there's my x equals -2, just like I got up here when I solved it analytically or using a little bit of algebra. Well, that's not the only way to solve this by graphing. Another way I could solve this by graphing is I could have waited until I moved it all over to the left-hand side. So I could have waited and said, okay, why don't I just move everything to the left-hand side and graph that? So here's that graph. And then I want that to equal 0. Well, y equals 0 is right here. So those intersect right here and right here, which just so happens to be -4 and -2, which is what I was supposed to get. So another option is to move everything to one side and just find the x-intercepts. Just find the x-intercepts. But no matter how I choose to solve it, I see that there's only two numbers in the domain that make this a true statement, -4 and -2. All right, so let's keep that in mind and let's try to apply those to a trig equation. Now at this point, we've graphed trig functions. We have graphed, for example, the sine function. So let's try to solve this equation right here. Let's try to solve this equation right here. Sine of what number's x will equal 1/2. Let's try to solve that, but let's solve it by graphing since we just got done talking about how to graph the sine function. So let's choose that graphing method. So I'm going to graph sine of x. Let's do that real quick. Sine of 0 is 0. Sine of pi over 2 is 1. Sine of pi is 0. Sine of negative pi over 2 is -1. That's 0. So there's one period of sine, and if I keep going, this will be -1, this will be 0. -3 pi over 2 sine would be 1. All right, so there's the sine function. Now let's go graph y equals 1/2, which is right here. So here's where y equals 1/2. Well, as we can see, these are going to intersect right here, right here, right here. They would intersect again right here. It's going to intersect an infinite number of times. So that's pretty different than what happened back up here. Back up here when we did it by graphing, the two graphs only intersected twice, and I had two answers. Down here, these two graphs are going to intersect an infinite number of times. So that's quite different. So where do they intersect? Well, it turns out the first intersection point's right here at pi over 6. So that's 1 pi over 6, 2 pi over 6, 3 pi over 6, 4, and again at 5 pi over 6. But then they're going to intersect down here. So this would be 12, this would be 13 pi over 6. They're going to intersect again at 13 pi over 6. And then it's going to intersect again at 1, 2, 3, 4, 5, 6, at -7 pi over 6. But it's going to intersect an infinite number of times. Those are only the ones I can see on the part of the graph that I drew. So it turns out that x is going to equal a whole bunch of numbers. Well, what numbers? I don't know. How can we figure this out? Well, for example, it's going to equal pi over 6. And if I add 2 pi to that, if I add 12 pi over 6 or 2 pi to that, I get this answer over here, which is 13 pi over 6. So there's got to be a way that I can kind of figure out what all these answers are. But for now, what's important is there's a whole lot of answers, an infinite number of answers. So as of right now, I can see -7 pi over 6. I can see pi over 6. I can see 5 pi over 6. I can see 13 pi over 6. But there's a whole bunch of answers. There are an infinite number of solutions. Well, that makes things a lot trickier than, say, solving quadratics was. So how many intersection points are there? There's an infinite amount. How many solutions? Well, infinite amount. There's an infinite amount of solutions to sine of x equals 1/2. Well, could we give a formula that would give me all those solutions? And I think we can. So let's think about what those solutions were. So if this is our circle, here's our circle, the unit circle for me. I prefer the radius to be 1. And sine equals a half right here at pi over 6, because this coordinate is root 3 over 2, 1/2, with a radius of 1. But sine also equals a half over here at 7 pi over 6. They both equal a half right there. Okay, well, the other answers I got were 13 pi over 6, but that's the same terminal side, right? That's if I'm at pi over 6, and then I come back around to get 13 pi over 6. But I also got the answer negative, what answer is that? Oh, I labeled that one wrong, didn't I? It's like, wait a minute, something's not right here. So this is 5 pi over 6, and then this one, that's negative 7 pi over 6. So every single answer I get is going to come from those two terminal sides. So one way I could write my answer is I could say, all right, x could be pi over 6. That's one of my answers. But I could add 2 pi to that and get right back to that terminal side. Or I could subtract 2 pi from that. So essentially, I could add 2k pi, where k is any integer. But x could also be 5 pi over 6. And I could add or subtract 2 multiples of 2 pi to that to get right back to that terminal side. So I could also add plus 2k pi, where k is any integer. Now that's a lot to write down. So a slightly quicker way would be to say x is pi over 6 plus 2k pi, or x is 5 pi over 6 plus 2k pi, comma, k is an element of the integers. So we could write it like that. There's lots of ways we could write this. We don't have to use a k either. We can use any letter we want to stand for that constant. But what's important here is there were two terminal sides on the circle that both gave me the ratio I wanted for sine. I wanted sine to be a half, right? I wanted sine to be a half. And once you find those terminal sides, there's an infinite number of angles that have those terminal sides. So we have to account for all of them because all of them are answers to this equation. So that leads us to a way to solve trig equations. What I need to do is take my equation and try to isolate the trig expression. I want to isolate the trig expression on one side of the equation. That way I know what ratio I'm looking for. Then I need to go find all the angles in one period that have that value. Basically draw the picture and go find all my terminal sides. And then I need to add k pi or 2k pi to get all the other ones, to get all the other coterminal angles that would also have that ratio. All right, so let's give it a try. So for this first one, we want to solve 2 cosine squared minus 1 equals 0. So I need to isolate the trig ratio. So I'm going to add 1 to both sides, then divide by 2. And then I want to isolate cosine, so I want to get rid of that squared. I want cosine, not cosine squared. So I'm going to find the principal square root of both sides. I'm going to get absolute value of cosine is equal to square root of 2 over 2. I'm going to solve that equation and get cosine of theta is equal to square root of 2 over 2, or cosine of theta could be negative square root of 2 over 2. Well, now that I've isolated the trig ratio, I know what I'm looking for. So now I can go to my picture, right? I can draw the circle. The circle helps with everything. So now I can go draw my circle. So here's my circle. It's not a perfectly drawn circle, but that's okay. I'm going to do the unit circle. I tend to prefer the unit circle. And I want cosine to be root 2 over 2. Well, that happens right here at pi over 4. Right? That's where x is root 2 over 2. The radius is 1. And that also happens down here. That also happens down here at 7 pi over 4, because that coordinate is root 2 over 2, negative root 2 over 2. So the cosine ratio is root 2 over 2 for both of those. Well, as I see here, I also want cosine to be negative root 2 over 2. Well, negative root 2 over 2 occurs right here at 3 pi over 4, that terminal side. And it occurs right here at 5 pi over 4. Because, how do I know that? Because this coordinate is negative root 2 over 2. So x is negative. This is negative root 2 over 2. So it turns out there are 4 terminal sides that give me the ratio that I desire. I'll move this out of the way. So there are 4 terminal sides that will give me the ratio that I want. I want cosine's ratio to be root 2 over 2 or negative root 2 over 2. Now the question is, how do I write all those answers down? Because there's a lot of answers. There's an infinite number of answers. For example, pi over 4 works, but so does 9 pi over 4. So if I draw 9 pi over 4, that is all the way around back to that terminal side. So that also is going to give me the cosine ratio that I want. So, I mean, there's a ton of answers. So how do I come up with all of them? Well, we just need to be clever, right? We need to use what we know. So here's what I know. I know that if I take pi over 4, if I take pi over 4 and I add pi to it, I get 5 pi over 4. In other words, if I take this answer and add pi, I get this answer. So adding pi gave me another answer. Then if I add pi to that, I get 9 pi over 4, which is another one of the answers that I should have gotten. So adding pi, so taking one of these answers and adding pi keeps getting me back to another answer. Now, why is that? The question is, why does that work? Well, look, this terminal side and this terminal side form a straight line. And straight lines, we know, have measures of 180 degrees or pi radians. That's why this works. So the quickest way to write the answer here, not the only way, notice I'm not saying the only way, the quickest way is to say, well, theta can be pi over 4 plus multiples of pi. So I could add 1 pi to get to here, or I could add 2 pi and get back to here, or I could add 3 pi and get back to this terminal side. So I could add multiples of pi. But if you look, the same thing's going to happen with these other terminal sides. This terminal side and this terminal side also form a straight line. So I could do 3 pi over 4 plus k pi, where k is an element of the integers. Now, that's not the only way that I could write down that answer. If I wanted to, it'd be a longer way to do it, but I could say, okay, no, that, I don't want to think through all that, Mr. Franklin. Can't I just say it's pi over 4 plus 2k pi, which would take care of every single answer I get from this terminal side? Yes, you could. But then you have to do that for each terminal side. So then you would have to do 3 pi over 4 plus 2k pi, 5 pi over 4 plus 2k pi, 7 pi over 4 plus 2k pi. K is an element of the integers. I mean, you could. That is an acceptable answer, but man, it's a lot longer and a lot more to write down. So, but I'll leave it up to you. It is an acceptable answer, sure. I mean, it gives you all the answers we need. Let's try another one. Oh, wait, there were more to the directions. I apologize. It said find a formula that gives all the solutions, then find 8 of the solutions. Okay, so I need to read the whole directions there. So this is called the general solution. This is called the general solution. It gives all infinite number of solutions. Okay, so that's called the general solution. So how do I use it to get the answers back out though? So then the directions say, then go find 8 of these. I don't know if we're going to do 8. 8's a lot. But then it says go find 8 solutions. So if you want specific solutions, then plug in integers for k. That's what k is keeping track of, as an integer, because you want multiples of pi. So for example, I could plug in k equals -2, and then I'd get theta is pi over 4 plus -2 times pi. So if I do that arithmetic, that's -7 pi over 4, which is a solution. That does work. Try it. Cosine of -7 pi over 4, so that would be, boom, that'd be √2 over 2 squared would be 2/4 would be a half. A half times 2 is 1. 1 minus 1 is 0. Ah, that actually does work. So that is a solution. But then I could plug it into the other one, 3 pi over 4 plus -2 pi, and get -5 pi over 4. That's another solution. That's the solution that I'd get by doing that one. Then I could plug in, say, k equals, I don't know, I could plug in k equals 0. That's an integer. So then I would get plus 0 pi plus 0 pi. I'd get pi over 4 and 3 pi over 4. But those were answers we found ourselves, right? Those are the ones we found ourselves. Pi over 4 is right here, and 3 pi over 4 is right there. Then I could plug in, say, k equals 1, and I'd get theta equals pi over 4 plus 1 pi, which would be 5 pi over 4. But that's one of the answers I found myself, so I already knew that. And then I could do 3 pi over 4 plus 1 pi and get 7 pi over 4. That's one of the ones I found myself. So I can just keep plugging in different integer values for k, and it'll just keep giving me back specific solutions to this equation. So we found 6, right? If we go through and count them, there's 1, there's 2, there's 3, there's 4, there's 5, there's 6. It said find 8. You get the idea. I could plug in k equals 2, or I could plug in k equals 10. 10 is an integer, and see what those two solutions are. So we have to deal with this issue of there's an infinite number of answers, and we only want some of them. You know, sometimes we want some of them, sometimes we want all of them. All right, so on this next one, we don't want all the answers. I only want the answers that are 0 up to 2 pi. 2 pi not included, 0 is included. So I don't need them all. I only need the answers that are between 0 and 2 pi. So let's try it. Let's give it a whirl. So I'm going to divide both sides by square root of 3. So I would get cosecant theta is -2 over the square root of 3. And then if I don't want to deal with cosecant, I can do the reciprocal. So that means that sine would be -√3 over 2. Cosecant and sine are reciprocals of each other. So now let's go draw a picture, right? So let's go use our circle. Circle is always handy. And I want sine to be -√3 over 2. So that's going to happen like right down here and over here. So there's two terminal sides where that's going to happen. The first terminal side would be, let's see, that'd be pi over 3, 2 pi over 3, 4 pi over 3. And then if I keep going, I'm going to have it's going to happen again at 5 pi over 3, because basically I'm going left 1/2, down √3 over 2, right 1/2, down √3 over 2. Those are angles we work with all the time, right? That's 4 times, it's 240, so that's 180 plus 60. And then this is 360 minus 60, so that's 300 degrees. So that's 60 degrees in there. So we end up with those two terminal sides. Now, as we hopefully know by now, there's lots of angles that have those terminal sides. So I need to write a formula that gets me all of my answers. So theta could be 4 pi over 3, but I could add multiples of 2 pi to that. Theta could also be 5 pi over 3, and I could add multiples of 2 pi to that. And remember, k is an integer. We should always tell our audience what the heck k is. It's an integer. But here's the thing. As I plug different values of k in, I'm not going to get any other answers that are positive, so bigger than 0, but less than 2 pi. I'm not going to get any more of those. So let's try it. So if I plug in k equals -1, then I get 4 pi over 3 minus 2 pi. Well, that's going to be a negative angle. That's going to be -2 pi over 3. But that's not between 0 and 2 pi. That's a negative number. So I don't want that answer. It is an answer, but I don't want it. If I do 5 pi over 3 minus 2 pi, I get negative pi over 3. But again, I don't want that answer. It's negative. I want positive answers that are between 0 and 2 pi. If I plug in k equals 0, though, I get the two answers I already had found. And those are positive numbers that are less than 2 pi. So that is an answer. That is an answer. I want those answers. If I plug in k equals 1, I'm going to get 4 pi over 3 plus 2 pi. Well, that's going to be 10 pi over 3. The problem with that is it's bigger than 2 pi, so I don't want it because I only wanted answers that are smaller than 2 pi but bigger than 0. In other words, I want all the answers you get by going around the circle one time in the positive direction. And the only two answers that are going to do that are 4 pi over 3 and 5 pi over 3. Those are the two I already knew anyway. So my answer to this, the two solutions to this equation that I'm interested in are 4 pi over 3 and 5 pi over 3. There are an infinite number of answers to this equation, but there's only two that are between 0 and 2 pi. Let's try another one. So let's solve this one. This one's already by itself, right? Tangent theta is -√3 over 3. So this is already by itself. So when I go to do the circle, remember how this works. This is the same thing as √3 over 2 over 1/2. Nope, that's not right. I just lied. This is the same thing as -1/2 over √3 over 2. Right, because that's the same thing as -1 over √3, which is -√3 over 3 after you get rid of the radical. So basically, I want the y-coordinate to be 1/2 and the x-coordinate to be √3 over 2. And we have points that do that on our circle. So let's go find them. For example, I could be right here, right, where I go left √3 over 2 and up 1/2. That's y, that's x. So I would get that ratio. And that is at 5 pi over 6. But I could get the same thing right here if I went right √3 over 2 and down 1/2, because that's y, that's x. So I'd be right down here. And that is at 11 pi over 6. That's 11 pi over 6. So notice that those form a straight line. This terminal side and this terminal side form a straight line. So I could say, all right, theta is going to be 5 pi over 6. And then if I just add pi, I get to this other one. So I could just keep adding or subtracting multiples of pi to get more answers. But just like last time, I only want the positive answers between 0 and 2 pi. Or if the answer is 0, that's allowed too. Well, I already found those. When I was making my circle, I found them. It's 5 pi over 6 and 11 pi over 6. There's not going to be any other answers that are positive numbers that are smaller than 2 pi. Because if I keep going around the circle, those are answers that are bigger than 2 pi. And if I go in the negative direction, I get negative angles. So I don't want that either. So I already know what they are. It's 5 pi over 6 and 11 pi over 6. Now, could I use the general solution to get those two answers? Sure you could. You get them by plugging in k equals 0. K equals 0 will get you 5 pi over 6. And then k equals 1 gets you 5 pi over 6 plus pi, which is 11 pi over 6. And that is smaller than 2 pi, so that is one of the answers we want. However, we got those by drawing the picture already. So, I don't know that you need to use the general solution to do that. All right, let's try this one. Now this one, that looks more complicated, but if you look closely, it's actually just an equation in quadratic form. So I could factor it. I could say, well, this is just 2 sine theta times sine theta. And then to get a 1, I could do 1 and 1. To get a negative 3, I could have these both be negative. So if I multiply this back out, I get 2 sine squared minus 2 sine minus sine is minus 3 sine. Negative, negative make positive 1. So I really just have 2 sine theta minus 1 equals 0, which means sine theta has to be a half, or sine theta minus 1 is 0, so sine is just simply 1. But notice I only want the answers that are between 0 and 2 pi. So again, I don't really need to do the general solution if I don't want to. If I just think about the circle and go around the circle in the positive direction, I'm going to find all my answers. They're all going to be there. So for example, sine equals a half right here at pi over 6. It equals a half right here at 5 pi over 6. Sine equals a 1 right here at the top at pi over 2. So I'm going to get 1 answer, 2 answers, 3 answers. That's it. Those are the only angles I'm going to get where sine's a half and sine's 1 for positive angles between 0 and 2 pi. So theta is going to be pi over 6, pi over 2, and 5 pi over 6. There are lots of answers, but they're either negative or bigger than 2 pi. All right, let's try another one. So this one, I have a cosine ratio and a sine ratio. Well, that's not good. I don't want two different ratios I got to worry about. So let's use one of our fundamental identities. We know that sine squared plus cosine squared is equal to 1. In other words, sine squared is really just 1 minus cosine squared. If I move that over, so I'm going to do 1 minus cosine squared in here. Then I'm going to distribute, get 2 minus 2 cosine squared. Then I'm going to move everything to one side. And then I'm going to attempt to factor this like I factored the other one. Let's see if we can make that happen. So I could do a 1 and a 1, positive, positive. That would be 2 cosine squared. 2 plus 1 is 3. Oop, that works. So then 2 cosine plus 1 is 0, which means cosine is negative 1/2. And this simply says that cosine needs to be negative 1. Aha. Again, though, I only want answers that I get by going one time around the circle in the positive direction. So I don't care about all the answers. I just want the ones I get by going one time around the circle. So here's my circle. Here's my circle. I want cosine to be negative 1/2. Well, that would happen right here at 2 pi over 3, right? Because x would be negative 1/2 and y would be root 3 over 2. That's going to happen also right down here at 4 pi over 3. And I want cosine to be negative 1. Well, that happens over here at pi. So if I come over to here to pi. So I get 1 answer, 2 answers, and then 3 answers. There's an infinite number of answers, but those are the only ones that are positive between 0 and 2 pi. So I get 2 pi over 3, pi, and 4 pi over 3. Again, we could plug one in to check, right? I mean, we're not above that. So let's say I want to check the answer of pi. So cosine of pi is -1, so I get -3 plus 3 on the left side. Right side, sine of pi is 0, so I get 2 times 0. Well, that's a true statement. Left side 0, right side 0, true. So we're good. We are good. Let's try another one. So again, I got a cosine squared. I kind of want them all to be the same trig ratio. So let's swap out cosine squared for 1 minus sine squared. And then let's move everything to one side. Let's move everything to one side here. So if I move that over, it's sine squared. Move that over, it's negative sine. 2 minus 1 is 1. Now, this doesn't factor. This does not factor. Nope. I don't think it's going to factor using integers. So we could try the quadratic formula. So sine theta is negative b plus or minus b squared minus 4ac all over 2a. We get 1 plus or minus the square root of -3 over 2. That's non-real. So there are no real solutions. So this is a non-real number, right? This is non-real. So if I continue, I mean, we don't know enough. You guys haven't learned anything about trig functions and non-real numbers or complex numbers. We haven't done that. That's not part of our curriculum. So this has no real solutions. So we're not focused on those kinds of equations. I'm merely pointing out that not every trig equation has an answer. There are trig equations that don't have any solutions in the real number system. So this isn't our focus though. So don't expect to encounter lots and lots of trig equations where they don't have real solutions. That's not what we're focused on. Just wanted to point it out that it's possible. All right, so how can this get more complicated? Well, I mean, it can get a little bit more complicated, but not terrible. Not terrible. So for example, what if I had sine 2 theta equals 1/2? Well, we're not used to having a 2 in the argument. So why don't we make a substitution so we don't have to deal with that 2 right away? So why don't we let, I'm going to use alpha, the Greek letter alpha. We're going to let alpha equal to theta. So then I really just have sine of alpha equals 1/2. Sine of alpha equals 1/2. Okay, well, we did this one earlier, but I'll revisit. The sine ratio is 1/2 when you are at pi over 6 and 5 pi over 6. That's where the sine ratio equals 1/2. So alpha needs to be pi over 6 plus 2k pi, or alpha needs to be 5 pi over 6 plus 2k pi. And it says we want theta to be between 0 and 2 pi. Remember, we're trying to solve this for theta. Theta is the variable. But yet I've got this alpha in here. Well, alpha's done its job. Alpha's done its job. Remember, alpha is holding the place of 2 theta. So we've used alpha. Alpha's done everything it can do for us. So let's go back and plug back in 2 theta. So alpha is 2 theta. So let's come back over here. 2 theta is pi over 6 plus 2k pi, or 2 theta is 5 pi over 6 plus 2k pi. Divide everything by 2, and we see that theta's got to be pi over 12 plus k pi, or theta's got to be 5 pi over 12 plus k pi. So this is our general solution. This is the general solution, but that's not what we were asked for necessarily. They didn't ask us to come up with a formula that gave me every single answer. They asked me to find only the answers that are between 0 and 2 pi. So let's go find them. So if k is -1, what do we get? We get pi over 12 minus pi. That would be negative 11 pi over 12. That's a negative answer. I don't want that. 5 pi over 12 minus pi would be negative 7 pi over 12, but that's a negative answer. I don't want that. Okay, so those were a dead end. If k equals 0, I get pi over 12, and I get 5 pi over 12. Ooh, I like those answers. Those are positive and less than 2 pi. What if I plug in k equals 1? I get pi over 12 plus, I'm plugging in k equals 1, so plus pi. And I get 13 pi over 12. Ooh, I like that. That's less than 2 pi. 5 pi over 12 plus pi, that would be 22 pi over 12. Ooh, that's less than 2 pi, barely, but it is less. It is less. 12 goes into 22 less than 2 times. Now, I don't need to plug in k equals 2. That'll just be a dead end because I would already be adding 2 pi to a number, so I would be bigger than 2 pi. So that would just be a dead end. So I don't need to mess with that. So it turns out there are 4 answers. I wanted pi over 12. I wanted 5 pi over 12. I wanted 13 pi over 12. And I wanted 22 pi over 12. Those are my 4 answers. There are 4 answers between 0 and 2 pi for that theta variable. And I got them. Got all 4 of them. And it wasn't too bad. It wasn't a lot longer than the ones we did before. Notice the big difference. What makes this one different is the argument is 2 theta. So if the argument contains anything other than just theta, you could use a substitution like I did to solve that equation. So let's try another one. So see how the argument is not just theta. The argument of tangent is theta minus pi over 2. So you can start out by just simply saying let alpha be theta minus pi over 2. And then you just turn it into this equation, which is a little bit easier to solve. Tangent alpha equals 1. And we know that tangent equals 1 at pi over 4. So if you draw the circle, here, we know that at pi over 4, tangent equals 1. And we know that at 5 pi over 4, tangent equals 1. Those are the 2 terminal sides where tangent equals 1. So alpha could be pi over 4. And then to get to the next one, I could just add pi. So plus k pi. So if I just keep doing multiples of pi, I just keep getting more and more answers. Remember, k is integer. But remember, we're not actually solving for alpha, we're solving for theta. So alpha was holding the place of theta minus pi over 2. So theta minus pi over 2 should equal pi over 4 plus k pi. So if I add pi over 2 to the other side, I get theta equals 3 pi over 4 plus k pi. So this is my general solution right here. But I don't want the general solution. I want all the values of theta that are positive between 0 and 2 pi. 0 could be an answer, according to that. Those are the answers I want. So let's use this to go find them. So what if k was, say, -1? I'd have 3 pi over 4 minus pi. Well, that would be negative pi over 4. Ugh, I don't want that. That's a negative answer. What if k is 0? Well, then I get 3 pi over 4. That's definitely a positive angle between 0 and 2 pi. What if k equals 1? Well, then I get 3 pi over, that's some bad handwriting there, I apologize. I get 3 pi over 4 plus pi, which would be 7 pi over 4. Aha, that is definitely a positive angle between 0 and 2 pi. I don't want to plug in 2 again because 2 pi plus this will be bigger than 2 pi. So that's it. I mean, I've got all my answers. My answers are just simply 3 pi over 4 and 7 pi over 4. It's just those two values. There's only two values of theta that when I plug it into this equation, I get a true statement. That's not quite true. Let me rephrase. There are an infinite number of values of theta that solve this equation, but there are only two, 3 pi over 4 and 7 pi over 4, that are between 0 and 2 pi. That's what I meant to say. Okay. What if you have a ratio that you don't know? You can't get it from the circle. Well, then we're going to use a calculator. I mean, you know, that's how we roll. If we can't do it with the circle, we'll use a calculator. So for example, tangent theta equals 2. Well, I don't know where tangent equals 2. So if this is my circle, if this is the circle right here, here's y, here's x. I want tangent of what angle equals 2 over 1. Remember, that's y over x. So I want y to be double the length of x. Well, I don't know where that happens. That's not an angle we've been working with. So it's up here somewhere. I know that. So I go right 1, up 2. It's right there. There's one answer. And I know there's another one if I go left and down the same amounts. So if I go left 1, down 2, I'm also going to get a ratio of 2. So there's two answers. I just don't know what they are. But that's okay. That's okay. The calculator knows, right? That's what inverse trig functions do, is give me angles. So I know that one of the angles is inverse tangent of 2. So if I go grab my calculator, now notice it asked for the answers to be in radians. So I'm going to do radian mode on my calculator. So I'm going to go ask the calculator for one of these angles. And it tells me that one of the angles is 1 point, I'll do 3 decimal places, 1.107. So that's this one up here, right? The calculator always gives you, remember our restrictions. Inverse tangent is going to give me an angle between negative pi over 2 and pi over 2. So 1.107 is this one up here. So this is 1.107 radians. That's what angle's right there. So how do I get this one? How do I get this angle that this terminal side's on? I add pi, right? I add pi. So my general solution is 1.107 plus k pi, where k is any integer, right? That's my general solution. And I'm going to use the general solution to get all the answers that they've asked for. So if k equals negative 1, I get 1.107 minus pi. So if I do that, what's that going to give me? It's going to give me negative 2.034. Well, that's negative. I don't want it. So if k equals 0, I get 1.107. That's the answer I already knew from the calculator. If I plug in 1, I get, let's see what I get. Let's add pi. So it's going to be 1.107 plus pi. It's going to be, 4.249. That's another one I want. Now, remember 2 pi would be about 6.28. So any answer I get that's less than 6.28 is less than 2 pi. I don't want to plug in a 2 here because 2 pi plus this would be bigger than 2 pi. So my answers are 1.107 radians and 4.249 radians. You can switch them to degrees if you want, if you're curious how many degrees that is, but the answer was supposed to be in radians according to the directions, so that's what we'll do. Let's try this one here. I want secant to be negative 3.7, which means I want cosine to be negative 1 over 3.7. If you don't like that fraction, if that fraction makes you uncomfortable, then feel free to do that division on your calculator and write it as negative 0.27027. I have to round it. Got to round it. But I'll keep a bunch of decimals so I maintain some accuracy here. So again, if I draw the circle, I don't know where that's going to happen. I have no idea. I mean, I can get close, right? I want x to be negative 0.27, so that's negative 0.5. So I don't know, it's like right in here. So it's this terminal side, and then if I come straight down, it'd be this terminal side. So there's one answer. There's one terminal side, I should say. So here's one terminal side, and here's the other terminal side. Now the calculator will give me one of them. So if I ask the calculator for inverse cosine of negative 1 over 3.7, let's see what it tells me. It gives me 1.844 radians. That's this one. It's 1.844 radians. And then to get this one here, this blue one here, this blue terminal side, well, let's think about this for a sec. 1.844, that's this angle, which means it's also this angle, but negative. So to get the blue one, to get the one I've got in blue here, it's going to be all the way around the circle, 2 pi, and then I'm going to subtract off the 1.844. I'm going to subtract this chunk off of it, leaving me this blue chunk. So if I do that on the calculator, so if I do 2 pi minus, I get 4.439. So those are my two answers. Again, you could do the general solution here if you want. It's up to you. So you could say, all right, my general solution is 1.844 plus 2k pi, or it could be 4.439 plus 2k pi. K is any integer. But the moment I plug in a negative 1 here, this whole angle will be negative, so I don't want it. Same thing with this one. The moment I plug in 0, I get 1.844. I already knew that answer. The moment I plug in 0 here, I get 4.439. I already knew that answer. The moment I plug a 1 in, I'm going to get answers bigger than 2 pi. So again, I really just need the two positive angles I get from these two terminal sides. So as soon as I find those, I'm good to go. But you can do the general solution. It'll give you the same answers.